Hello, and welcome to this talk on Unambiguous DNFs and Alon-Saks-Seymour. My name is Siddhartha Jain, and this is joint work with Balodis, Ben David, Göös, and Kothari. The take-home message from this talk will be that we have a new and interesting Boolean function that might be worth your attention. And here's how I'll go about this. First, I will introduce the function itself. Then I will exhibit an interesting property that it has with the full analysis, which will turn out to be a solution to the problem that we care about in the end. I recognize that this is an unusual format for a talk, so I request your patience while I go through it. So what will our function be based on? It'll be based on a board game called Hex, which has shown up in mathematical literature before. This game is played on a grid of hexagonal cells. And in this game, both players take turns putting their pieces on the board. The goal for the white player is to create a path from left to right. And for the black player, it's to create a path from top to bottom. In this board, it looks like the white player has already won because he has constructed this path. A famous property of this board game is that it can never end in draws. So how do we create a Boolean function out of this? Well, first, we will be working with a grid of squares instead of hexagons for convenience. And the second and major difference that we will have is that we strip this game of its most famous property and we allow draws. So our input will be a Boolean grid of size n by n. Pictorially, I represent ones as black cells and zeros as white cells. And just like hex, the goal for player one is to build short vertical paths. And for player zero, it's to build short zero paths. Here, crucially, I require the paths to be short, where our notion of short would be of length at most 2n. So as you can see in the first input, player one wins this because he has a short vertical one path. In the second input, we have an example where player zero wins because he has this zero path. But how we define the function, it can end in draws even if there are paths, valid paths. And here is an example of a one path, which is too long to justify player one winning, and we call it a draw. So just like I said, our function will just be encoding who wins. Given an input x, this function maps it to 1 if player 1 wins, or in other words, there is a short vertical one path. Maps it to 0 if player 0 wins, or there is a short horizontal 0 path. And we just have a star otherwise to denote a draw. So here is a first interesting property of this function, which will be a sort of warm-up. The way we design this function, it's easy to certify when it's 0 or 1. By a certificate, I mean a partial assignment consistent with your input, such that it fixes the function to be a constant. So in both the 0 case and the 1 case, we can always just report the short path itself, and that serves as a certificate that this input is either 0 or 1. So I claim that we also designed this function such that it's hard to certify draws somehow. So C star of F is just the complexity of certifying a draw for the worst case input. So what is this input? It's not that hard to come up with. It's just a long winding one path of maximal length. Let's call it a snake, inspired by the Nokia game. So this is clearly a star input, or in other words, a draw, because there are no horizontal 0 paths, and the only one path is way too long. So, but what is the complexity of certifying that this is the draw? I claim that it's quadratic, which is essentially tight. And our argument here will be based on this notion of sensitivity. What do I mean? Well, for example, consider this bit, and let's say I flip it to a 0. Then what happens is that I can demonstrate this short horizontal 0 path that shows up as soon as I flip this bit. This means that on flipping this bit, the value of this function changes. And notice that almost all bits on this path are sensitive, except for the corner bits, which are only order n in number. So I claim that any certificate that this input is a draw must report all the sensitive bits. Else, if it doesn't, I could just produce an input consistent with the partial assignment where the bit is flipped. So we can conclude that it is in fact hard to certify draws in this game in the worst case. And this was pretty easy. But is this the question that we want to answer? No. And here's why. So note that this hardness that we showed was not balanced somehow or only one-sided. So here I define these new notions, which have not really been studied in literature before, as far as you know, of not 0 and not 1 certificate complexities. So what do I mean by not 0 certificate? Well, it's just the size of the smallest partial assignment consistent with the input, again, which fixes the function to be either 1 or star, but never 0. So what we proved was essentially this statement that there are quadratic many bits, which when flipped, change the function to be 0. So to certify that player 0 doesn't win, we need quadratic number of bits in the certificate. But if I only wanted to certify that player 1 doesn't win, then what I could do is the following. I could just report the first few rows of this input. And that's enough to certify that there's only one path emanating from the top. And it's definitely too long. So that motivates the actual question we want to answer, which is that we want to find an input such that it's simultaneously very hard to certify that player 0 doesn't win and player 1 doesn't win. And I claim we can still do this, although we lose quantitatively a bit. So here's my solution. I will just trade off the width of the snake from the previous example with the number of snakes we can fit into this grid. So pictorially depicted is essentially what I mean is that there are root n snakes of root n width each. So what's the not 0 certificate complexity of this input? I claim it's n to the 1.5. And similar to the sensitivity argument we used earlier, we will use something called block sensitivity. And again, by example, consider this block of bits. If I flip all of them at the same time, I can again demonstrate a short horizontal 0 path, which just goes through these bits. And any certificate that claims that this input is a draw, or in particular player 0 doesn't win, must contain at least one bit from this block. But there are omega n to the 1.5 number of these blocks, because Again, any non-corner bit on these paths, all these paths simultaneously, serves as a block. So it is hard to certify that player 0 doesn't win. But what about certifying that player 1 doesn't win? Well, we could try our original strategy of trying to report the first few rows. But notice that because the width of these paths is now root n, we would have to report root n many rows to serve as a certificate. So the total size of our certificate would be, again, omega n to the 1.5. And it turns out this is essentially optimal. The reason for this is that if there were less than n to the 1.5 bits read by the certificate, then by averaging one path has like small O of root n bits read there. And notice that we only really care about the 0 bits being read because the 1 bits can only help us. So let's say that this is the neglected spiral or snake, and these bits were read by the certificate. So my strategy will just be to greedily extend the path down, the one path starting from the top. So let's say I want to shortcut this curve and then this curve, but then I get stuck here because a 0 bit has been read. Well, I can just sidestep it and continue. And I will only be forced to sidestep smaller of root n times. So this means that I can change the input such that I get a player 1 wins. And that's it. So we established our goal of proving that this min of C0 and C01 can be much larger than C0 and C1. But what did we really solve? It turns out that this puzzle that we invented in the paper has a motivation because it's equivalent to a puzzle that has been studied before in literature a bit, which is this problem of separating the 0 certificate complexity from the unambiguous 1 certificate complexity. Let me define what unambiguous 1 certificate complexity or UC1 is here. Just like I can equivalently write the 1 certificate complexity of F as the least k such that F is a width k DNF. UC1 of F can be written as the least k such that F is an unambiguous width k DNF. Here, an unambiguous DNF is such that when it evaluates to 1, exactly one term evaluates to true. Or in other words, at most one term evaluates to true on any input. So this puzzle was introduced by Göös in 2015, who also achieved the first exponent greater than 1. But notice that our construction quantitatively improves on both previous works and is also vastly simpler. These constructions were pretty complicated, while our construction can be analyzed within this talk. So we were happy with this and we put it up on arXiv, but the story did not end there. Our most recent co-author, Kaspars, read our paper and introduced our separation to quadratic. And we later merged our papers, which resulted in the paper I'm presenting to you right now. And the punchline is that we've exhibited a function such that the 0 certificate complexity is quadratic in its unambiguous 1 certificate complexity, which is actually optimal. You cannot do better. And this resolves, has a lot of questions and has a lot of applications in communication, complexity, and graph theory. which motivated it in the first place, which I discuss now. So first off, this separation can be lifted to the communication mode. And this separation implies that the co-non-deterministic communication complexity of clique versus independent set is essentially like log square n, which is a tight up to lower order terms, a tight lower bound and upper bound known for a long time. It's pretty neat that this problem is known to be equivalent to a purely graph theoretic problem. This is the Alon-Saks-Seymour problem, and it asks if there exists a graph whose chromatic number is much, much larger than its biclique packing number. The biclique packing number here means what is the smallest number of bicliques you need to partition the edges of your graph. So as this table shows, for both of these problems, upper bounds were known a long time ago, but this paper, this work, culminates this investigation by proving essentially tight lower bounds on this problem. It's also worth mentioning that we have an interesting phenomena happening in our paper. So in the paper, we also mention a third puzzle 3, which is some problem of two coloring and intersecting hypergraph. We include this for purely aesthetic reasons. And the conclusion here is that we have a reduction from a combinatorial problem, the Alon-Saks-Seymour problem, to another combinatorial problem, puzzle 3, which goes through complexity theory. And in particular, this step uses the notion of lifting, and this step uses the notion, uses this cheat sheet framework, which is a big hammer in query complexity. So we went from a combinatorial problem to another combinatorial problem using tools which are inherently complexity theoretic in nature, and we don't know a direct reduction between these two combinatorial problems. And that's pretty amazing to us. So we also have more applications for this separation, which I listed here. One of them improves on a decades-old result. What's interesting here is that the last one actually uses hex, because intuitively our quadratic example is not structured enough to give this separation. And it would be interesting to try to improve the exponent for the hex function itself. Finally, there have already been some follow-ups and some applications of our work. So there is a notion of state complexity in finite automata, and there's an analogous question there concerning co-non-deterministic versus unambiguous finite automata. And our result has been applied pretty directly to prove certain new results concerning these. What's even more exciting is that there is a paper in FOCS this year which studies this notion of learning partial concept classes and uses our result to separate their notion from the classical notion of back learning. So that's all I had to say, and thanks for listening.